Hey Team Bio, welcome to your screencast and introduction to water. So we've been talking about the structure and function of atoms and elements, and last screencast you learned about the different types of bonds, covalent bonds, ionic bonds, and hydrogen bonds, and today we're going to be kind of putting it all together to talk about the relationship between structure and function of a couple different molecules. Okay, so let's review the definition, the biological definition of organic. So an organic compound or an organic molecule is a structure that contains covalent bonds. Not covalent, covalent bonds between carbon atoms, so carbon to carbon, or between carbon and hydrogen. So carbon H. Okay, so we're going to look at two different compounds, methane and water, and we're going to be talking about whether or not they're organic, and then we're also going to be talking about whether they are polar or nonpolar. Nonpolar means that the molecule is totally neutral all the way across. Polar means that there's an area of positive charge and an area of negative charge. Kind of like the north and south poles of a magnet. A polar molecule is going to have a north and south pole where it's either positively or negatively charged on one or the other end. Okay, so the first compound we're looking at is methane. Methane has the molecular formula is CH4. And the structure looks like this. We have carbon with 4 bonds to hydrogen. Remember, carbon is right here on the periodic table. It can take 1, 2, 3, 4 bonds to fill its outer valence shell. So it likes to make 4 bonds to be stable. And hydrogen take 1 electron to fill its outer shell. So it likes to make 1 bond to be stable. And that's exactly what we see here. Okay, because methane has bonds between carbon and hydrogen, this meets our definition of organic, so this is an organic molecule. Okay, let's look down here at water next. Water has the molecular formula H2O, and it has the following structure: 1 oxygen bonded to 2 hydrogens. Remember, oxygen has, it's got 8 protons and 8 electrons to fill its outer valence shell. It wants 2 extra electrons, so it can form 2 bonds to be stable. Hydrogen can form 1 bond to be stable, so thus its structure. Oxygen forming 2 bonds for a stable and full outer valence shell, and hydrogen each forming 1. Okay. Oxygen doesn't contain any covalent bonds between carbon or carbon and hydrogen, so it is an inorganic molecule. However, I should say inorganic. Maybe I should just erase molecule because we're going to be writing things below it. Erase that. Sorry. Okay. Water, however, is polar, while methane is nonpolar. And the reason for that is something that's called electronegativity. Electronegativity is the ability to pull on nearby electrons. Or I should say pull on shared electrons in the outer valence shell. Okay, and electronegativity has a trend across the periodic table. We're going to take the noble gases out of this situation. Their outer valence shell is already full, and as a result, they are really stable and they tend not to make bonds with anyone. They're just flying solo. Electronegativity tends to increase as we move across, it's called a period. So one row within the periodic table. So it's increasing in this direction. The reason for this is, let's look at the second period right here, because it's a little bit easier to see the trend across the periodic table. As we move from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, what makes these different is that this lithium has 3 protons, whereas fluorine has 9 protons. And so the ability of lithium to pull on electrons, because it only has 3 positive charges, is less than the ability of fluorine to pull on electrons because it has 9 positive charges in its nucleus. And they share the same valence shell, so their outer electrons are the same distance away from one another. So fluorine, it can pull, because it has more positive charge, it can pull on those electrons more strongly than the 3 measly protons that's in lithium. Okay, so that's why electronegativity, the ability to pull on outer electrons, is increasing as we move across the periodic table in this direction. The trend is also that electronegativity increases as you move up a group. So it's increasing in this direction as well. And you might think, that doesn't make very much sense, because down here, I don't even know what this element is, but it has 85 protons. Why is electronegativity increasing as I move up a group? And the reason for that is that as you move down the groups, the valence shells get further and further away from the nucleus. So the ability, even though the elements that are way down in this corner of the periodic table have tons of protons in their nucleus, their outermost electrons are really far away from that nucleus. So they can't, because they're just so distant, they can't pull on those electrons as strongly. So it's increasing as we go up a group and as we go across a period in this direction, which makes fluorine the most electronegative element in the whole periodic table. So, but oxygen is up there. It is right here. Oh wait, no, sorry. It's right next to fluorine. It's, now I can't move this. Gotta erase it. Oxygen is this one. It's the second most electronegative element in the periodic table. Okay, and then hydrogen is all the way down here. And carbon is right here. Okay, so these are the three that we really care about in terms of their electronegativity. I want you to know that oxygen has more electronegativity than hydrogen and carbon. And that hydrogen and carbon has slightly more, but it's like, we're talking measly, a paltry difference between carbon and hydrogen. They're very close together. Okay, so because carbon and hydrogen have really similar electronegativities, it means that these electrons that are in this, oops, I guess I should say what this is first. Okay, these lines, I think we talked about this last class, or last screencast, but this is a covalent bond. Okay, this covalent bond actually represents two shared electrons. And because neither carbon or hydrogen can pull on these electrons more strongly than the other, they have very similar electronegativities, we see that these electrons are shared equally between the two of them. And this is true for every covalent bond in methane. So as a result, it is non-polar. Okay, let's compare that to water, H2O. As we said before, oxygen is the second most electronegative element on the periodic table. And so as a result, it can pull on electrons in a covalent bond very strongly. So what happens is that the electrons that this covalent bond represents they end up spending a lot more time closer to the oxygen than they do to the hydrogens. So oxygen ends up with a slightly, this is a delta, and it's a shorthand, it's a scientific shorthand, and it means slightly. Oxygen ends up with a slightly negative charge. It's not a full negative charge. It's not like an ion, which has lost or gained a complete electron. It's only slightly positive because these electrons that are in this shared pair, this bond, spend a little bit more time closer to the oxygen than they do to the hydrogens. And because the hydrogens, their electrons are being, these shared electrons are being pulled away from them, they are slightly positive. And this is what we call a polar molecule because it has two sides. One side that is slightly negative and one side that is slightly positive. Okay, I think we're going to end this screencast here and make this part a separate screencast because then it's going to be too long if I keep going. Okay, that's all.